Welcome back. Well, in the last video, we took the Maclaurin series for cosine of x, the Maclaurin series representation. So I guess we might as well do the same for sine of x. And I'm sounding very nonchalant, but I have a reason behind why I'm doing this, and you'll see in a few videos from now when we come up with the grand conclusion. So anyway, let's just set f of x. And you might just want to do this yourself, and instead of watching me do it, because it should be pretty self-explanatory now that you saw cosine of x. But and then you can check your work. You can pause right now, and then you can check to see that we got the same answer. And you'll probably be right, and I probably made a careless mistake. So f of x is equal to sine of x. So first of all, let's just figure out all of the derivatives of sine of x, and we can already guess that it probably cycles similar to cosine of x, with slight variation. So what's the derivative of sine of x? Well, that's just cosine of x. What's the second derivative? I'm just going to stop putting parentheses around these numbers. The second derivative, well, that's just the derivative of that. It's minus sine of x. The third derivative of x, well, I guess I'll put the parentheses so you don't think it's f to the third times x. The third derivative, well, that's just going to be the minus cosine, right? Because the derivative of sine is cosine, but then we have that minus sign there. Then the fourth derivative, well, derivative of cosine is minus sine, but we have a minus there, so we get back to sine. And then the cycle continues. And so the fifth derivative is just going to be cosine of x, or just the derivative of sine of x. And then the cycle will continue, right? All right, so we know the derivatives, and we could just keep going. So let's evaluate the derivatives of our function of sine of x at x equals 0. So f of 0, well, that's sine of 0. What's sine of 0? Well, sine of 0 is 0. F prime of 0 is equal to cosine of 0. Well, that's equal to 1. The second derivative at 0, that's minus sine of 0. Well, sine of 0 is still 0, so that's 0. You can see it's a very similar pattern to what we saw in the Maclaurin series for cosine of x. And then the third derivative evaluated at 0, that's cosine of 0 is 1, but we have a minus sign, so it's minus 1. This you already know, the fourth derivative is 0, sine of 0 is 0, and then it starts to cycle again. The fifth derivative, 0, equal to 1. So we start with 0, then positive 1, then 0, then minus 1, then 0, then positive 1. So every other number is a 0. Every other, I guess you could say, coefficient in the Maclaurin series is a 0. The coefficient when you don't include the factorial term. And then the ones in between oscillate between positive 1 and negative 1. So what would be the Maclaurin series for sine of x? The Maclaurin series representation. So we could say that sine of x, and remember, I haven't proven to you that the Maclaurin series representation of sine of x or cosine of x or e to the x really is equal to those functions over the entire domain. I might do it later. Frankly, I've been thinking about the proof myself. It hasn't been completely intuitive how to do that proof. Although if you test them out, it does seem to make a lot of sense. But you shouldn't just take my word for it. I'm going to look up the proof, and I will prove it to you eventually. But for now, you just have to take it as a bit of a leap of faith that the Maclaurin series representations just don't approximate those functions around 0. That when you take the infinite series, it actually equals the function. So sine of x, the Maclaurin series representation, is going to be equal to, well, f of 0, well, that's 0, plus f of, so the first derivative is going to be 1 times x to the 1 over 1 factorial, which is just 1. This is just 1. And then we have, this is just plus 0. And then we have minus, and now this is the third derivative, right? So minus 1 times x to the third over 3 factorial. And then we have a 0. And then we have a plus 1. And this is now the fifth derivative, so x to the fifth over 5 factorial. And we'll just keep going. But I think you see the pattern. So let me rewrite it. Sine of x is equal to 0. So we get x to the first. So that's just, well, x minus x to the third over 3 factorial plus x to the fifth over 5 factorial And then you can imagine the pattern, we'd go minus, we're just taking the odd numbers, x to the 7th over 7 factorial, plus x to the 9th over 9 factorial, minus x to the 11th over 11 factorial, and we'll just keep going, right? And so we'll just keep oscillating in sign. That's a bit of a pun. And we use all of the odd exponents. So if I were to write that in sigma notation, I would say, well, that equals, and sigma notation often is the hard part. Well, once again, let's see, the first term, when the term is 0, well, this is the first term, right? And we get a positive sign. So we want, because we're going to oscillate in sign, we're probably going to take negative 1 to some power. So it'll be negative 1 to the n plus 1, because we want every, so let's see if that works. If this is the first term, this will be a, no, that won't work. It'll be to the 2n plus 1. And actually, I think I should have done that in the previous video too. I think it should have been negative 1 to the 2n, not negative 1 to the n. I'm sorry for that mistake. Right, so it's negative 1 to the 2n plus 1 times x to the 2n. Oh, no, sorry, I was right in the previous video. See, I'm confusing myself because I don't count the 0 terms. So you probably help me to write the sigma down first. So this is equal to, as you can see, I do all of this in real time. Infinity from n is equal to 0. And so the first term is positive, so it'll be negative 1 to the n, right? Because negative 1 to the 0 power is 1, right? So that's positive. And then the second term is negative, then positive, negative, right? Times. And so what is the 0th term is x. So it has to be x to the, let me see, 2n plus 1. Does that work? Right, because the first term would then be 3. Right, x to the 2n plus 1 over 2n plus 1 factorial. It's almost easier when you just write it out like that. Well, that's pretty interesting. But what's even more interesting is if you see the similarity between the Maclaurin series representation for sine of x and then the representation we figured out for cosine of x in the previous video. We figured out that cosine of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. So they're almost the opposite, right? They almost complement each other. The cosine, these are all of the even exponents, right, and even factorials, and sine is all of the odd exponents, and because this is x to the 0, right? So that's why you get 1 here. And in sine, it's all of the odd exponents and all of the odd factorials in the denominator. So that by itself I think is pretty neat. And what is especially neat, just another fodder for thought, is that we know from trigonometry that sine is just a shifted cosine function, or that cosine is just a shifted sine function. But what's neat is by shifting it by pi over 2, which is all they are, right? If you were to graph it, they're just shifted 90 degrees to the left or the right of each other. You can actually represent them differently by essentially picking the odd or even, I guess, terms of kind of this factorial polynomial series, whatever you want to call it. But anyway, it doesn't matter if you didn't understand what I said at the end, as long as you appreciate how cool this is. I will see you in the next video.